Okay, right, this is the core practical, CP3. This is where we're going to measure the internal resistance of this cell. So just to run through the equipment, we obviously need our cell in a cell holder. We've got a voltmeter, we've got a variable, it's a rheostat, but we're going to use the rheostat as a variable resistor in this one. We're not going to use it as a potentiometer. And finally, we've got a multimeter because we need to measure current, but the current is going to be small. The current is going to be in milliamps, so we need that high degree of resolution, so we need the multimeter. Okay? So, if you remember from the circuit diagram, we have a single series loop where we have the cell, the ammeter and the variable resistor all together in one series loop, like that. Okay, so as you can see already, we've got a current. The cell is driving a current of around about 34 milliamps through the variable resistor. And no surprises, if we change the value of the resistance, the current changes accordingly. Now, just a word of warning here. If you remember, when we measure milliamps, okay, there's a maximum upper limit of 200 milliamps. If we go above that, the internal fuse blows in the multimeter. So as you can see, as I'm changing the resistance, the current is changing accordingly. Okay. Now, we need the voltage as well. Now, like I explained in the previous video, it doesn't matter whether you measure or attach the voltmeter here or here. It's going to measure the same voltage because there's going to be no resistance in the wires and no resistance in the ammeter. Okay, so I'm just going to actually connect it across the variable resistor because it's easier to see what's going on. And there we have the voltage across the variable resistor. Make sense? So far, so good? Right, we're ready to vary. Now, before you start varying voltage and measuring current, it's always good to see what sort of range you're going to be getting. Okay, so let's take the resistance up here. So we're going to start with a very small current. Yeah, so it looks like the smallest current is 25 milliamps. Now we can take the current up. Remember, we can't go above 200. Almost. Okay, so basically that looks like that's out around about up to about 160. So we need, for a graph, general rule is, you know, eight data points, 8 equally spaced data points on a graph will give you a nice graph. And we're seeing a fairly decent range of V as well. So let's start at the bottom end. Okay, we're getting a slight fluctuation here. That's just because the slider is kind of like half on, half off. Right, we're looking at 25.4 milliamps and a voltage V of 1.42. We're looking at a current of 26.7 and a voltage of 1.41, would that be? Okay, let's go a bit further. Get up to 30. That'll do. 30.6 milliamps, 1.41. Let's go up in tens. 40 milliamps, 1.39. 40.8 milliamps, 1.39. Let's go up to 55. 55.4 milliamps, 1.37. 65.6 milliamps, 1.35. 83.7 milliamps, 1.32 volts. 108.4 milliamps, 1.28 volts. 125.9 milliamps, 1.25. Oops, this is where the current does jump up quite considerably. 144.3 milliamps, 1.21 volts. Starts to jump around a bit. 183.5 milliamps, 1.15 volts, and we'll leave it there. Okay, your job now is to plot a graph. If you remember, we're plotting a graph of V on the y-axis and I on the x-axis. You're going to draw a straight line of best fit, and the gradient is minus R. Don't forget, this is in milliamps. Right, your gradient has to have current in amps if you want your resistance, your small r, your internal resistance to come out in ohms.